Alrighty, let's do this. So, we are at week 10, and week 10 we're going to talk about binary trees. Okay, so binary trees are basically a type of graph. Okay, but we're going to get to graphs later. So it's basically like a linked list, but instead of having one link after the other, you have, let's see if I have some pictures in there. That's the PowerPoint. I'll let you look through this PowerPoint. So this PowerPoint is from the Carano textbook. It's got a bunch of things in it that are not really about trees. They're talking about hash tables and those kind of things that we haven't covered yet. And I have a couple of links in there to visualize a tree when you add something to the tree, those kinds of things. So, but what you want to do is you want to look at your textbook and you want to look at the binary trees, okay, and read through this thing. And what are binary trees? Okay, so
sorry, is this Carano?
This is LaFour.
That's LaFour.
Yeah, this is the LaFour. So if you read through the LaFour, he does a pretty good job as usual to explain these things. So what is a tree? Well, it's like the folder system on your computer. That will be an example of a tree. In fact, let me look at this PowerPoint that I have in here, so we can look some of this stuff. So yeah, this is the one from Carano. You can stay if you want.
That work.
Okay. Yeah, so this is an example of a tree. It's basically like an organizational chart is an example of a tree. Some kind of a family tree is an example of a tree. The folder system on your computer will be an example of a tree. All right, and so this is the tree. All right, so there's a couple of terms as far as trees are concerned. You have a root, which is basically the main thing all the way at the top. You have edges, which is the connections between these different nodes. Okay, so each of these is a node, right? So this is a node, this is an edge, node, 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 and there's different levels, right? So in this particular tree here, we have 4 different levels. This is not a binary tree because a binary tree will only have 2 children. This is your parent, the one all the way at the top, the root is a parent, and these other ones underneath it, right, are its children. And in a binary tree, you only have 2 children per parent. Okay? See ya. You can have subtrees, right? And let's go back to this one here. Nope, not that. There you go. Okay. So again, we have edges, we have nodes. This example here is not for a binary tree. A binary tree will be just 2 leaves per parent. Okay, and again, here are some of the terms again, the different levels. What's a parent? What's a child? What's a root? Right? This example right here is an actual binary tree because notice each parent only has 2 children at most. It doesn't have to have 2 children. So the ones all the way at the bottom, they don't have any children underneath them. So H, E, I, J, and G are leaf nodes. So what are the leaf nodes? Well, there are nodes that do not have any children. Okay, so any node that does not have a child is called a leaf. Okay, and again, the connections between the different nodes, those are your edges. And yeah, you can have subtrees. You can have a path. Path is the way you're going to traverse the tree to get to the actual, node that you need to find. Okay, and again, the root is all the way on the top. There is a rule that there should be only one unique path for you to go from a parent to, or let's say from the root to some kind of a child, right? In other words, if I wanted to go from A to I, the only way for me to go through A through I is A, C, F, I. If there happens to be another way that I can do this, then it's not a valid tree. So what's wrong with this picture here? Well, there's multiple ways for me to get to this one all the way to the left, right? I can go from here to this one, or I can start from here on the top, go to the left one first, then go to the left one here, and then I go in this direction. That's second way I can get there. I can also go from here to there, to there, to this one, and then another way. So there's different paths to this particular child or a leaf, and that does not make it a real tree. Okay, this is more of a graph. Okay, so basically, what you're seeing right here, this non-tree is a type of a graph. The graph is basically a tree is a subcategory of a graph. Okay, it's just one type of a graph. All right, and then again, the terminology: parent, child, leaf, subtree, visiting. Right, visiting just means you got to that one. Traversing means going through them. Levels, or you can see what the levels were right in the picture. These are the different levels. Level 0 is your root. Level 3 is the last one with all the leaves. And other thing is keys. Keys are the actual values that we have stored in each of these nodes or links, right? What we used to call links in a linked list, now they're called nodes. But it's basically the same kind of concept. You're going to have a class. You're going to have it linked to its own object type using the same way that we did the linked list. And in each of these nodes, we can have data. Like we had the integer data or the double data, or we can have a whole bunch of different data, right? If you want. So those are the keys. Okay. So what is a binary tree? Well, a binary tree is a tree that has only 2 children. Okay. And not just that, but the way that these are arranged is the left child is usually, if you wanted to have a binary search tree, notice the relationship. The left child here, right? We have a 53 all the way at the top, then you have 30, then you have 72. So the left child is always less than the parent, and the right child is always greater than the parent. Right? So notice 53, 30 is to the left of it, 72 is to the right of it. Then when you have the 72 parent, you have a 61, which is less on the left, and you have an 84, which is greater there on the right. Then when you go one down, then the next one is less than. If it's going to be less than, it goes to the left. And the same thing applies for all the other ones, right? 30 is here, you have 14 to the left, 39 to the right. 39 is bigger, 14 is less. And the same thing applies to all of them. Okay?
Why is that?
That's just the way we're going to. So basically, just like we had like when we have our data structure for a queue, right? It was an array, and we can of course do whatever we want with an array. You can tell it insert anywhere you want. So this is basically, by the way, trees can also be implemented with arrays. And we're just saying that okay, the way we're going to be inserting things in this array of objects is, well, if you have a parent, you're going to insert to the left. So it's basically it's a fixed rule of how I'm going to be inserting these things into the tree. So that's just the rule. And the reason we have that rule is that it becomes very easy for you to find the smallest, the node with the smallest element. So can you tell me where's the node with the smallest element here? All the way to the left. What about the node with the biggest value? All the way to the right. So there you go. So it makes it a lot easier. And you no longer have to go through all these different numbers to get to the one you need. You just go 1, 2, 3 jumps, and then you get to the smallest number. So it's a quick and efficient way for you to get the min and the max out of an arrangement of items, if you want to call it that. Okay. And again, it talks about how your computer system is an example of a tree, the workshop, the applet. We're going to skip that part, right? An unbalanced tree. So unbalanced trees get created whenever we are inserting trees in a predictable manner. Like if we're going to be inserting things in always in ascending order. So let me go back to the visualized tree. Maybe I have it in there so you can see it. Okay, so I have, I'm going to insert 1. So this is my value 1. Then I'm going to insert 2. It's going to go to the right. Then I'm going to insert 3. It's going to go to the right. All right, I'm going to insert 4. All right, so now I'm creating an unbalanced tree. So if I keep inserting them in the ascending order or in descending order, let me go and put a -1. All right, put another -2. Oh, I don't think it lets me do a minus. That's why I inserted it there. Okay, so I don't think it's, yeah, so it's not doing minus. No, minus is disabled. Okay, so that's why I put it in there. So the way it works is it checks to see is the 1 greater than or equal to 1. If it's greater than or equal to, then it's going to try to insert it to the right of it. Then it's going to compare this one here. It's going to look at this one, and it's going to say, is 1 the one that I'm trying to insert? Right? The one that I'm trying to insert is the 1. Where is it going to go? It's going to go on the left here. Okay? So the bottom line is you create unbalanced trees by not randomly, by not having just a randomly generated numbers. If you're inserting an ascending order or in descending order, right? Let's go descending order. So I'm going to go with 10. Then I'm going to do, let me zoom in on this thing. Right, 10, 9, right, 8. And that is basically an unbalanced tree. Okay? So there you go, unbalanced tree, and we create unbalanced trees by having a very predictable order in which we insert these things. Okay? And yeah, you can read through this, representing a tree in Java. Okay, so here's your tree node, right? So just like we had a link for our linked list, we're going to have a class node, right? And what's going to be in that class? Well, some data, right? And it's going to have a left node and a right node, right? And there's a typo in here, I believe. This should be a capital node. Okay, so you have a left child, you have a right child. So how is this different from my linked list? Well, the linked list only had, well, unless we were talking about a double linked list, right? The linked list had only one, next or whatever. Okay, if we're talking about the double linked list, we had a next and a previous, but they were still kind of linearly arranged. They're not, they're not in a hierarchy of, sorts, or not in a chart order, if you want to call it that. And if you wanted to, you can combine the data. So if you have like a huge volume of data, it's not just one little field, you could put all those together into another class and then have a reference to that class inside your node. So basically all your data is grouped inside of one class, and then that's what this is. And then inside of the node itself, we're talking about just how these things are connected, left and right. But for simplicity's sake, but what we're going to do is we're not going to do it this way, right? We're just going to stick with this original one here that we have on top. Okay? The tree class. So the tree class is basically similar to how we had our circular lists or whatever. You had your circular list class, which had a circular, which had a link first. Well, this is similar to that. Instead of a list, instead of a link, you have a node. Instead of first, you're calling it root. So it's just a way for you to know where the whole thing starts. Just like when we had, in a circular list, it wasn't first, it was current. But when you have a double-ended list, you had a first and a last. When you had a single, list, it was just first. Okay. And the actual tree app class is just inserting different links in there and finding a link, those different things. Okay, so first of all, how are we going to find a node? Okay, so the way it's going to work is, I'm trying to see the code. So this is my code, right? We're going to be looking for a key, which is some kind of a value, right? We're going to start a node current, which is equal to the root, so start this thing all the way at the top, And then what we have to do is we have to have a loop that goes on until you basically find the key, right? If you find the key, this thing stops. If you haven't found the key, if the key, the value that you're looking for, is less than the current, then you're going to go to the left, right? That makes sense since left is always smaller. And otherwise, you're going to go to the right. Make sense? Not that hard. And if you get to a current equal to 0, then you basically got all the way to the bottom, right? So when would a current be equal to 0? Well, when you got to the bottom, all the way at the bottom of the leaves, when you say the bottom one, you go tell it go next. There's no next, the next is 0, and then that means you got all the way to the end. Okay, and then you stop. And otherwise, if you can find it at if at any point your current data becomes equal to the key, this loop stops, and then you return the current. So it's not very complicated. Okay. Inserting a node. Again, what you have to do is let's see the code for that thing. Okay. So again, we have we're going to create a new node. We're going to give it some data, right? If the tree is empty, if the root is equal to 0, then make the root equal to that new node. Otherwise, what you're going to do is we're going to have to find where to place this new one, right? And this is the answer for your question. Why is this thing arranged the way it is? Because of this insert, right? Because of how we have defined this insert. So what is going to happen is you're going to start current at the root, and you also want to have some kind of a reference to the parent. Okay, so basically you want to have one below and one on top of it. And you go like before. So if the value that you're trying to insert is less than your current data, then you're going to go to the left. If at any point you basically get all the way to the left as far as you could, then you're going to make the parent left child equal to that new node, and then you're going to stop the whole thing. And similarly, the else is basically if your ID is greater than the current data, you're going to be going to the right. And current is equal to current right child if you can't find it, right? So keep moving to the right until you find it. If you get all the way to as far right as you can, right? When current becomes equal to 0, then you're going to go and tell it parent right child is equal to the new node. Okay? And that's it. So that's the insert. And by the way, we reset parent is equal to the current in the beginning of this loop, and then current moves one step forward. So that's what I was telling you. The parent is one level higher, and the current is one level lower. So that's that. So that's the insert. Traversing the tree. There's different kinds of traversals. And they're actually, you could implement these with recursion, and you can also implement them with regular loops. And if you look at the class webpage, I don't know if I have it, or if I don't have it, just look at, if you just Google the Computer Science Club webpage, you're going to see, let me see if I can find it. All right, if you go to the Computer Science Club webpage, right, on the right I have a link for internships and work. Okay, and under that internships and work, oh, and by the way, to mention to you, the vice president was asking me if I can get students to go on a field trip to IBM. So if you guys are interested, let me know. I'm not sure when that's going to be, but as soon as I find out, I'll let you know. And if you're interested, we can go and have a tour of the IBM facility. And hey, what's up?
Sorry for interrupting.
No worries.
Can I get the key to your office because our club stuff is there.
Yep. Would you be interested in going to a tour to IBM?
Oh, what? A tour?
Yeah.
I'm down.
Okay, cool.
That's in South San Jose?
It's in Coyote Valley.
Oh, the one off Staley?
Yeah.
Okay. When is
You're
it?
interested? I'm not sure yet, but the vice president was asking me if
The
if
vice
I can get.
president of IBM?
No, the vice president of our college.
Oh, I was
Yeah.
like, dang.
No, but we're trying to set up a partnership with like IBM to get things going and all that good stuff.
Oh.
So they want somebody like a good student to ask good questions. So
Yeah, sure.
you should-
When is it?
I don't know. We're trying to set it up, but yeah, I'll let you know. I'll let you know. Awesome.
I'll get you.
I'll see you.
Thanks.
All right. So, hope he doesn't take my car. All right. So, going back to this thing here, if you go to the computer science internships and work, you're going to see this, right? A whole bunch of links in there, and these are, they're pretty good. So if you're interested in finding an internship or job or whatever, go through these different links. And if you're interested in the kind of questions that they might be asking, look at underneath prepare for the interview. And then on top of this, there's lead code. I don't know if I told you about lead code. Well, I'll tell you again if I didn't. Right? This is lead code, and it shows you all the kinds of different problems that were asked by a lot of these top employers. Like what questions were asked by Google, what questions by Facebook, Amazon, etc., etc. But not just the questions, but the actual solutions to these problems also. Some of them are really easy, like add two numbers and that kind of things. And some of them will probably have to do with data structures and trees and these kind of things that we're talking about. Anyway, so in one of these links that you're going to see in here, the one on right here, so there's a book basically to show you what these questions are and how to solve them and all that good stuff. Right? This is the book. Okay, it's very highly rated, so it's a good book to have. And other than that, there's also this link right here. Top 10 algorithms for coding interview, right? So this is basically like a compilation of all these different ones. And I lost it, but I'll go to it. And top algorithms, you go to that. There's a whole bunch of them right in here. And solutions too. And this is conveniently for us, this is Java. All right, so this is all in, as far as I've seen, it's pretty much all of it in Java. And it talks about, look at it, there's a whole section on trees, right? Tree traversal, pre-order, in-order, post-order, level order 2, vertical order. So those are some of the questions that, we're not going to cover every single one of these, but there's where the answers are if you want to look at it, if you want to look at it in more detail. So if I look at tree traversal, this is what I wanted to show you. This is a traversal algorithm for traversing this tree right here. So you have this tree, 5, 4, 8, 11, 13, and all that stuff. And it might not be a regular binary search tree, because I'm not sure if this applies. 11 is kind of not less than 4. So I don't know what it's doing there. But whatever. Okay, maybe it's in, I think it's in, no, I don't know. Whatever. The point is, there's two different ways for you to traverse a tree. One way is if you wanted to use a loop, right, which may be a little bit easier to understand, but you can see that it's quite a bit longer, and it actually requires creating a queue, right? And you can create a queue using the build linked list. What happened there? You can create a queue using the build linked list. What happened with this thing? Oh, there we go. I clicked it.
Thanks.
Cool. No worries. Do you need anything else?
This is good.
What's that for?
The Halloween party.
Okay, cool.
Yeah.
Have fun. All right. So this implementation here uses a queue for you to visit all the different nodes and push them on the queue and so on and so on and so on. And you can see it takes quite a bit of code to get that going. Or if you wanted to use a recursion, this is how much shorter it becomes. Okay. So this is the recursive way to do it. So we're going to look at, for simplicity's sake, the book tells you we're going to use recursion. And there's different order in which you can go through these trees. And then, by the way, again, as you can see, that's a common thread throughout these questions, like right away for you to traverse the tree in a certain particular way. So it might be beneficial for you to, if you can't derive it, maybe try to memorize, how to do these kind of things, especially before the interview. Okay? So anyway, what we're going to do here is, this is going to be an in-order traversal. And what we're going to do is, we're going to be visiting the nodes in ascending order based on their key values. Okay? And because of the arrangement of the tree, where the one that we defined it here with the insert order of things, if we do it this way, if we call a traverse function here, and this is going to be a recursive, right? We're going to have a recursive call right here to go all the way to the left. Then you're going to visit the node, and then you're going to have another recursive call which goes all the way to the right. If you do it this way, then you're going to visit all of these in a in-order traversal. And what does it look like? Well, this is the code right here. All right. So if the local root is not equal to null, right? And again, this pretty much works on the big tree, and then it goes to a subtree, and then a subtree, and then a subtree, and a subtree. That's why we're talking about a local root. Okay. Basically, until the subtree is empty, what you're going to do is you're going to tell it, okay, well, call yourself, but then this time go and make the local root equal to the left child, right? Then you're going to, when you get all the way to the end, when local root is no longer null, that's when you're going to stop calling it. And then the next thing that's going to show, after we're done with the recursive calls for this piece, we're going to show the data. So we're going to go all the way to the left, and we're going to show that. We're going to show that first data. Then we're going to return. We're going to show the next one, and the next one, and the next one. And then we're going to do the in-order recursion for the other side, okay, to go to the right. So that's the traversal of in-order of a tree, okay? And if you want to visualize this thing, all right, this is, we have 3 nodes. We have an A and a B and a C, right? First, what we're going to do is we're going to call in-order B, right? Call in-order B goes to, and then I think that might be in this here too. Is it? No. No, not in there. Okay. So what we're going to do is we're starting at the A, right? We're going to call in order B, right? We're going to the B. Call in order is going to be null here, right? Because there's nothing left of the B, right? So we're going to go to the null. We're going to return back. And then as soon as we return back from this first one, we're going to visit B. Then we're going to try to go to the right of it. There's nothing there. So we're done with this call. That means now we're going to go back to the original one, call in order B. We're done with this one. Then we're going to visit the A. So we visit B. Then we're going to visit the A. Then we're going to go to the right, which is my C node now. And we're going to do the same. We're going to do the same business. We're going to try to go to the left. That's going to take us nowhere. We're going to come back. Then we're going to visit the C. Then we're going to try to go to the right. That's not going to take us anywhere. And then we're done. Okay? So that's the in-order traversal. Okay? And there's an applet in there. Oh, these are the numbers. That's what I was looking for. All right? So this is the order of things. If we're starting at 50, all right? We start at 50. First thing we're going to do is we're going to go to the left. We're going to go to the 30. Then we're going to do another recursive call. We're going to go to the 20. Then we're going to do another recursive call. There's nothing here. We're going to return back to the 20. We're going to show it. So now this is the 4, right? We're going to actually show the 20, visit the 20. Then we're going to go back. Then the next thing is we're going to try to go to the right. That's going to take us nowhere. Then we're basically at this point, we're done with this one. We're going to return back to this one. Then we're going to visit. After we come back to this one, we're going to visit the 30. Then we're going to go to the right. Then we're going to try to visit this. There's nothing here. We're going to show the 40. That's the 10. Then we're going to try to visit this. There's nothing in 11, right? There's nothing here. So we're done with this one. Then we're going to come back to this one. And we're going to go back to the 50, right? So now we're at the 50. So we already went all the way to the left. We're going to visit the 50, right? That's the next piece. Then we're going to go to the right, 60, try to go to the left. There's nothing here. Return, visit the 60, go to the right, there's nothing there, and then you're done. You basically come back to the original where it was called. Question?
Yeah, the 30.
Mm-hmm.
Writing code. I forgot what it was called. What was that?
Node.
Called the parent, or was that the subroot?
Each of these is a node. So this is the root. The 50 is the root. This is the child of the root, right? And it's also the parent of these two. And since these two do not have children, they're called leaves.
Yeah.
Right? So the ones all the way at the bottom are leaves. The ones that don't have any children are leaves. Then you have on top of them their parents, and then all the way at the top is the root, and the connections are the edges. Okay?
When you visit the node, is that when you print it out?
Mm-hmm.
The code that you
Yeah.
print out?
Yes.
When you visit?
The visiting part is when you do this. Yeah. And of course you can do other things too. You don't have to just show it. You can do whatever you want, right? Okay. So yeah, and there's like all the different steps if you played through this. There's other traversal algorithms. They're not always as useful as this one. So one way to traverse a tree is this right here. And again, traversing trees is not something that you do a whole lot as far as binary trees are concerned. It's more applicable when we're talking about when we start talking about graphs. When we talk about graphs, then it matters. And what's a graph? Well, a graph is basically a tree that can have multiple connections between nodes, right? For a binary tree, we need to have only one unique path from root to a specific leaf, if you want to call it that, or node, right? In a graph, you can travel multiple ways. And what are graphs used for? Well, they're used for, let's say if you have like some kind of a map and you have a bunch of cities and you're trying to figure out what's the quickest way to go from point A to point B in that map. And that is actually useful when we're talking about networks, when we're talking about traversing the internet. That's what this is the kind of algorithm that the actual routers are using to determine what's the quickest way for the packet to travel from source to destination. Okay, and in that case, we have also different search algorithms like breadth first search and depth first search and all kinds of different ones, right? But those kinds of traversals are more applicable when we get to graphs than when we're talking about trees. Like the primary reason of a tree is really kind of sort of to easily find min and max. That's really the main thing. Then later on, you're going to see there's another kind of a tree. It's called a heap, and it's basically the same thing. It's a tree, but now the biggest thing, because of the arrangement of how we are going to insert things into the tree, either the highest or the lowest value is all the way at the top. Okay, which allows us to do things like heap sort, so that you can, basically the smallest thing will always move itself all the way to the top. Even if we remove it, then the next smallest thing is going to just rearrange itself all the way to the top. So there's something called a heap sort where you can basically pack a whole bunch of numbers into a heap, which is a type of tree, and then by just removing them one by one, you're going to remove them in either ascending or descending order, depending on whatever's on top. Okay? So that's that. And pre-order and post-order traversals, they're used for these kind of algebraic expressions. So you have infix, which is what we're used to, right? A times B plus C, and that can be represented as a tree, right? This is my A, this is the time, there's the plus BC, and there's a prefix and postfix notation, right? The prefix notation, the multiplication is first, then you have the plus BC, and the postfix is you have the ABC, and then the plus and the multiplication. Okay, so these can be simulated using these algorithms for traversing a tree. So if you were to visit the tree first, and then do the recursive call to the left, and then you do the recursive call to the right, then you'll be doing a pre-order, okay? And which is basically a way for you to generate this prefix notation. So that's the pre-order. Okay? And if you wanted to do it the other way, which is the postfix notation, which is this right here, right? Then you could do it this way. You could call the recursive left, visit recursive left first, then visit recursive right, and then visit the nodes. Then it will generate this kind of a postfix notation. Okay?
So these aren't really equations, they're just pathways.
Yeah, you could say that. Well, the pathway is how it is it's basically the order in which you visit these. That's what this is. Okay.
Oh, just a follow-on question.
Yeah.
So, I understand the infix, the prefix, you write it out, what it's actually doing, it's not doing math?
No, it's just visiting. It's just to visit. Yeah.
No mathematical calculation.
No.
Because the infix, it looks like there's some mathematical calculation, B plus C, and then you multiply the result with A.
Yes.
You're saying in the prefix.
Well, you could do the math after you visit. Remember, the visit for the simplest case is you just show the thing, but then other than showing the thing, you can actually do math along the way.
Can you do the math for the example prefix and postfix? Just what is math there?
For the prefix and the postfix,
Yeah, on the example that you have.
what do you mean?
Well, prefix says star A plus B
Mhm.
times C. So do you do the B times C first, and then you add A?
Yes.
And then you multiply
Yes.
by what?
Yeah. Well, it's look at the original. No, it's B plus C first, and then it's going to be the A.
Yeah, I got that one.
Yeah. So, well, that's that. They're all going to work in that same.
Does the star represent multiplication, or is that?
It's the multiplication. Yeah. So you multiply A times C, or sorry, it's A plus B plus C. So you do this first, right? And then once you do the B plus C, then you multiply the result times A. Yeah?
Okay, so the addition sign, it isn't saying add A to.
So it's basically start right to left. These two are going to be added. Then the result of that is going to be multiplied. So then you have the result of B plus C here, which is, let's say, a number D, right? Then you have AD, and then in front of it you have an asterisk. So now the next thing you're going to do is you're going to multiply A times D, which is the result of B plus C.
Got it.
Okay?
So the addition is saying you're adding B plus C.
Yes, you're adding B plus C.
And
So
then the multiplication is multiplied by A,
yes.
the result.
Yep.
All right.
So we start right to left, right? We do B and C are the things we're going to be working with. We're going to be adding them. We're going to get some result D. Then you're going to have asterisk AD. Again, we work right to left. You're going to work with D and A, and you're going to multiply the two.
Yeah.
Okay?
Okay, sorry, so can
Yeah.
you go through the postfix as well?
Postfix. All right. So postfix. What was the original thing? We have an A times B plus C. Okay, so on this one, A times B.
So this is more like machine language. It's
Yeah, it is
first
machine.
variables, and then you do the first operand, and then you take the next variable and you do the next operand.
Yeah, there's actually explanations right here. So BC plus means apply the last operator in the expression to the first and second things, right? The first thing is B, the second thing is C, so this gives us B plus 6, right? Inserting this in the original expression, postfix gives you this, okay?
Thank you.
Yep.
Got it.
Okay, so those are the trees, and then finding the maximum and the minimum nodes. How do you think we're going to find the minimum node?
Or left.
Start at the top, go left, 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 left. When you get all the way to the node, you found the min. Finding the max, you start at the top, go right, right, right. When you go all the way to the right, and there's nowhere further to the right that you can go, then you have found the max. Okay, and this is one of the primary applications for trees. Deleting nodes is the more complicated thing to do. There's different things to do. One is if the node to be deleted is a leaf, it has no children. The other one is if the node to be deleted has one child, and the other one is if the node to be deleted has two children. Okay, so the first case is the node deleted has no children, and all you have to do is just change it to no, basically. Okay, so I have, I'm trying to delete, what am I trying to delete here? Oh, and again, because of the Java garbage collection, we don't really have to delete anything. As long as nothing refers to a particular node, the Java garbage collection will just wipe it out from memory and recover the memory eventually. So what we're trying to delete is, yeah, we're trying to delete the 7, right? So we're going to look for the 7, we're going to get to the 7, and if the 7 does not have any children, all I'm going to do is I'm going to make the parent of the 7 equal to null, and then the actual node 7 is going to get cleaned up by the Java garbage collection. Okay, so that's that one. And this is your code. Again, you want to have a current and a parent, right? So that the parent is one above. To handle this thing, you're going to keep finding it. So this is delete nodes. We give assumes non-empty list. Delete no children. Find. Okay, so this one is finding it. And if current is equal to null, you got all the way to the end. Return false. You couldn't do it. You basically couldn't find the thing. Otherwise, you go left or right, and that's pretty much it. Okay. Okay. And the actual, this is if they're both null, right? So this was what we said. If the parent, if the one on top, if the one you're trying to delete has no children, what you're going to do is you're going to make equal current equal to the root, and the root replies to your subtree's root. Okay, and along the way, you have to check this. You have to change this boolean is left child to true or false along the way. Right, so if you're going left, is left child is true. If you're going right, is left child is false, right? And based on that, you change either the parent left child to null or the parent right child to null, right? So this last piece right here is the actual deleting. Okay, so if this is your parent, and if this thing has nothing, if you're going to the right and this thing has no children, then simply make the parent's right node equal to null, right? So that's this piece here, right? And otherwise, if you're going to the left side, then you make the left child equal to null. Okay. Now let's look at the node to be deleted has one child. Okay, so here it is. We're trying to delete 71. Okay, so before we do the 71, well, after we do the 70, so this is before we do 71, this is after we do the 71. So what we're going to have to do is we're going to have to move each of these one up. Okay, so the 63 is going to move where the 71 is, and the 67 is going to move back up to the 63. Okay, and there is your delete for that as well. There are 4 variations. So there are 4 variations. The child of the node to be deleted may either have a left or right child, and for each of these cases, the node to be deleted may be either the left or right child. Okay, so again, this is one of those things, just like the linked list, you're going to have to maybe redraw it and visualize it. It's hard to explain with words, really. So if no right child, we're going to replace with left subtree, right? If there's no left child, we're going to replace the right subtree, and the node to be deleted has 2 children now. All right, so this is the other case. All right, so what I have in here is I'm trying to delete 35. 35 has 2 children. It has a 30. It has a 40 also. Okay, so what we're going to have to do is we're going to have to shift them up a little bit, but there's intermediate steps along the way. So what's going to happen is, let me zoom out a little bit. So you're starting with a 50, 25, 50, 35, and then this stays the same. The 30 moves up here. And I thought we were trying to delete the 35. What are we deleting?
25.
We're deleting the 25? Oh, my bad. So we're deleting the 25. So the 30 is going to have to get moved here. And 35 stays where it is. 40 stays where it is. And that's the end of the delete. Okay? So the best thing to do really is just get the code and write it out step by step and follow it just like we did with the linked list, right? Draw the pictures every step of the way. See how the picture changes so that you can see it. Okay, but these are a little bit more involved than I think pretty much everything else we've done up to this point because it involves recursion, and recursion is a confusing thing. Okay, so that's pretty much as far as I want to tell you about trees. Okay, there's also trees represented in arrays. There's a relationship. Okay, the right child is if you have a parent with a certain index, the left child is going to be 2 times the index plus 1, and the right child is going to be the 2 times the index plus 2. Okay, and if you are at some kind of a node that has a certain index, then you can easily find the parent of that. And we're talking about if we're going to be doing this with arrays, and again, we can do it as linked lists or node list if you want to call it. But this is if it is with an array, then the index minus 1 divided by 2 gives you the parent of every particular node. Okay, and here it is, a little picture that shows you, all right, this is my 50. That's the first one. Then you have the 25 and the 75. That's the 1 and the 2, right? And how they correspond to the different elements of arrays. Okay? So arrays can also be done, trees can also be done using arrays as well. Okay? So what do you have to do for this? The assignment that I have is actually pretty simple. What I ask you to do is just get the program and find the min and the max. That's it. Okay? Not very complicated. So it should not be an issue. If you wanna go in more detail, I'll be happy to draw some more pictures. Come see me in the office hours, or send me your questions. And yeah, that's pretty much all I want to tell you about trees for today. We're good? I hope. We'll find out soon enough. I have a feeling that I'm going to be drawing pictures soon enough. Okay. Okay, so I think just the deleting piece is the most complicated part. Right, so that's the one that's going to require me to draw the pictures, maybe not. Okay, so yeah, that's all I have for today, and yeah, we're almost getting towards the end of this. I'm going to talk about hash tables next time, heaps, graphs. Then we're talking about when to use which one, and then the last couple of weeks are just catch up and turn in the assignments. And yeah, don't worry. I have made it a little bit easier and easier with every week. As you can see from the binary trees, I didn't make it very hard. So I'll do similar thing with heaps and the graphs as well. Okay, I might even throw in some built-in data types of Java so that you can use the built-in structures.
It goes through the hop code, but you're not going into that.
No, I'm not going into that.
So trees, parklands, page.
complete tree, yeah, complete 3 Java program. Yeah, this listing 8.1. Wherever the listing 8.1 stops, that's where I stopped it. Okay? So that is what I have to tell you about trees. And then yeah, there's the Karana PowerPoint also to look at. And yeah, read LaFour. That's the key for this one. And then draw some pictures if you have to.
And the display function also seems to display like a binary tree.
Yes. Yeah, the display, you remember there's an in order, a post order, and there's different orders of traversal. But I think it's just an in order that you need to do. Okay? Just go with the listing 8.1. All right. So that is all I have for today. Send me your emails. Come see me in the office. You know the drill.